morning, everybody. Welcome to the Simon Center, or welcome back to those who were here before. It's always a pleasure to have many high school students, and in fact, these lectures are organized thanks to the generosity of the De La Pietra families, and their non-negotiable condition is that one of the 3 lectures provided by the speaker is given to the high school students. So that's why we disrupt you from your studies, bring you to the Simon Center. Hopefully you will enjoy the lecture, and eventually you'll be given some lunch and sent back home. Anyway, today we have a wonderful mathematician, Persi Diaconis, who is an expert in statistics, in probability. He was even a professional magician, and he's going to tell you about how randomness may run your life. Please.
Thank you, Paul. Hello, and this thing is working. You can hear me. That's good. I'm a professional mess maker. I study the mathematics of making a mess, and that has to do with, and of course, all of you are pretty good at that too. But I do it as part of mathematics, and then eventually you start to think, what does it mean to say that something is random? I mean, what does that mean? The world is so complicated, and how do we think about that? And for many people, for me, and probably for many of you, one of the closest things to a really random phenomena is that. Just take a coin and, do that. And it comes up heads or tails, right? That's random, right? And many of the images of randomness that we use start from that kind of physical randomness. But there's a question you could ask. Think of having a coin, and if you knew where you hit it and how hard you hit it, then you'd know how fast it goes up, and Newton would tell you how long it takes. If you know what its position and velocity is, Newton tells you, how long it takes to fall down. And you also know how many times a second it's turning. And so if you could carefully, calibrate, flipping a coin is physics. It's not random, it's physics. And so I'm going to talk about that a little bit, or try to, if I master this gadget. So what am I going to tell you about, just so you don't think it's too philosophical? I'm going to talk about flipping a coin, and then I'm going to talk about a way that we make math out of it, which is called a method of arbitrary functions. And then I'm going to talk about something, a little bit of philosophy, and then I'm going to try to answer a question that I don't hear asked so often in math talks, which is who cares? But so let's get started. So coin tossing is physics, and so when I flip the coin up, it has a velocity, how fast it's going. And say, feet per second, miles per hour, something like that. What's its velocity? And then it has a rate of spin. How many times is it turning over? And so a given flip can be graphed as a point on an axis. In this one, the velocity is pretty high, but the rate of spin is low. It's close to 0. That dot is close to 0 on the y-axis. And so well, in that case, the coin is going up pretty fast, and so it'll come down, but it doesn't spin very much, and so maybe, it won't turn over. And so there's a part of the initial conditions, the velocity and rates of spin, where the coin never turns over. If there was a dot way up there, the coin has terrific rate of turn, but it hardly goes up at all, so it doesn't turn over. And there's a region where the coin doesn't turn over at all, and it stays the same way as it started. And then there's a next region where it turns over just once and just twice. So you can make careful physics out of that. What's the curve of that region? It's a hyperbola. And so you should be able to make a machine that does it. And I made such a machine. I had my physics department make such a machine. It doesn't show perfectly, but I hope you can see it. It's oop, I didn't want to do that. Let's go there. It's a kind of gadget about this big, and I'll show you a close-up over there. There's the coin goes there. There's a cup, and there's a spring, and there's the coin on the spring, and you turn a ratchet, and the coin, you know, then the spring gets released, and ping, the coin comes up, and then there's the coin. Maybe you can see it up there. The coin's going up, and it goes up, you know, 1.5 feet, and then it lands in the cup, ta-ta, and it does land in the cup, and it always comes up heads. And it's the damnedest thing you ever saw. That is, I mean, you know, we're used to coins being random, and you go, ping, heads, ping, heads. You know, 50 out of 50, 100 out of 100. It just bothers you viscerally some way. Something's wrong. But of course, there's nothing wrong. The coin's hit with the same position, with the same force, and of course it does the same thing. So, you know, coin tossing is physics. And when I given this talk, I used to bring that gadget with me. And it takes a couple of hours because it wouldn't be terrible on this table. It needs a real lab bench because it has to be very rigid. And it takes sort of 2 hours to set it up. But nowadays, if you bring that through, you know, the airlines, what is that? Oh, it's a coin tossing machine. Sure. You know. Yeah, okay. But I have one, and I've written about it, and if you want to see all kinds of careful analysis of the physics of flipping a coin, and I'll talk a little bit about it. This is the phase space of coin tossing, and you know, this is the region of velocity and rate of spin. This black region, the coin, you know, doesn't turn over at all. The next region, it turns over once. The third region it turns over, you know, twice exactly. So the initial conditions are serrated in this way. And the first thing to notice is, as you get away, if you flip the coin vigorously, so you're around here someplace, the regions are very close together. So tiny changes in your thumb and the initial conditions make for the difference between heads and tails. And that's really what makes stuff random in some sense, that small changes in initial conditions make for the difference in the outcome. So a question is, okay, that's a nice picture, and you know what a coin flipped is. When we really flip real coins the way I just did, you know, where are we on that picture? That's a question. So that's an advertisement. I'm not just telling you about it. I wrote a paper about it, and if you wanted to ever read up around the dynamical bias in the coin toss, and it does more sophisticated things than I'm doing, than I'm going to be able to do here. But I'll tell you a little bit about what we did. So how do we figure out where we are on that picture? When I do that, you know, how fast is the coin going? It's not so easy to guess or have a feeling for that, you know, in miles per hour or feet per second. And so what I did, I thought, well, I'll take a high-speed, slow-motion, you know, camera, and I'll get movies of it, and then I'll be able to do that. And we eventually did that. But at the time I wanted to do it, nothing that you have access to will capture a coin. You have to shoot around 1,000 frames a second. It's not, you need, so it's where I was at Stanford, the only camera that would shoot at 1,000 frames a second was owned by our football team. And I talked to them, and they said, yeah, we could let you have it in the summer when the teams aren't. And of course, you'll have to hire our operator, and it'll be $700 an hour. And you know, I wanted to know the answer, but I didn't want to know it that badly, right? So, so I had to think about it. And so the first thing I did was do little experiments. I had a friend who with a stopwatch, and I would go 1, 2, 3, and when it left my hand, he would flick it, and when it landed again, he would flick it, and we did it for quite a while, and it took 7 hours actually to try to get, because you have to synchronize, and it's, real experiment of that sort. It's not so easy to measure the data, but a coin, the way I'm flipping it, a 1 foot flip type coin, it's going up about 5.5 miles an hour. So that's a number. Then I had my first good idea, which is I painted the one part of the coin white and the other part of the coin black, and then we got a tunable strobe light, blinks like that. And so I would go like that, and you would turn the strobe light until it was blinking at the same speed that the number of times that the coin was rotating, the same frequency. So when the coin froze, I would have it right or right within, it could be off by a factor of 2, but that was way, way off. And so that sounded like a good idea, and we tried it. And one thing is, again, 7 hours of fiddling, no kidding. The coin never froze. It would slowly turn, we would get it better, but of course I'm flipping a real coin. There's some variability in my flipping, and it never really froze, but we got some idea. And a coin, when it's flipped, is it 100, is it 15? A coin, when flipped, makes something between 15 and 20 revolutions, and it takes about half a second. That's not very much variability. That is, it's half of that, so it's between 8, 9, 10. A coin, when you flip it, is flipping over something like 8, 9, or 10 times a second. And so it's not as variable as you might think. Then the first good idea was I took a very, very flexible flat ribbon. It was a piece of dental floss, about 3 feet long, okay? And I attached it to the coin, carefully, and there it was. And then I did that, and then I unwrapped the ribbon so that I knew how many times it was flipping, so I could check. Now, of course, if you're careful, there's a difference between a coin flipping and a coin with a piece of dental floss flipping. Those are different things. But didn't seem to make much of a difference. And eventually we did get cameras. And if you go to my website sometime, you can see pictures of 1,000 frames a second, and then in slow motion of coins flipping and what they actually do. I'll tell you a little bit more about that when we get there. Now I put this gadget down, and it's not good to let it roam free. Well, let's see. So we've been, talking about coins for about 15 minutes. Here are 10 more things about coins. Okay, well, I'll be faster about them. The first thing is, when people are careful about it, like people who gamble on real coin tosses and stuff like that, they often do something like this. They shake the coin, and then they flip it. Okay, and does that help? Well, you can prove, as math, that random in, random out. That is, if you start with the coin 50-50 heads or tails, and then you flip it, by ordinary flips, randomness is preserved. So it helps in that sense. Now, the analysis that I'm talking about neglects air resistance, and that's a question that is, there's air there, right? Does that affect the analysis? And my physics friends took me to Hoover Tower, and they made me drop a penny over the side, and you can watch a penny flutters when it falls down. Does that? So then there's a lot of approximations and talk about Reynolds numbers and things of that sort. And it seems to be that a 1 foot flip, air resistance, you don't have to worry about it. It would be harder to do. I mean, it's a different kind of math to analyze, how that slows things down. The analysis that I made, assumes that the coin starts out, flat, parallel, and then flips over through a plane like that. And that's all questionable because, your hand is, your hand. I mean, and I'm not a perfectionist and so forth. Trying to define when the coin lands, that's how long it takes to hit your hand. It's tricky and complicated. No bouncing. So, the other way, if it was important, maybe people do that, right? And the coins go around like that. I'm not doing that. I'm catching the coin flat in my hand, and that's a complication. Okay, here's a funny fact. Coins can land on their edge. Of course they can. Now, does that actually happen? Well, I had it happen to me when I was a little younger than around high school age. We were making a bet, and some tricky bet, taking advantage of people who don't know about probability, oops. We were shaking 10 coins out and then throwing them on the table and counting and then doing that again, and we were going to do it 1,000 times or something like that. And one time, the coin, spun around on its edge, it hit the table, I mean, and it landed, it stayed on its edge. And so it can happen, and it did happen to me. And in fact, there was a PhD thesis in the physics department about what's the chance that a coin lands on its edge. And they concluded that an American nickel lands on its edge with chance about 1 in 6,000, and I'm neglecting that. Sorry, but I'm neglecting that. Let me say it a little bit differently for a second. Does everybody here know what a Toblerone is? It's a long chocolate bar like that, right? And then okay. So if I had a Toblerone and I threw it up, it has 3 sides. 3 long sides, and it'll land on one of those 3 sides, and if I tumbles around, it's never going to land on one of the 2 edges, right? I mean, they're tiny. Now, suppose I start eating it, as I would be likely to do. Well, when I eat it toward the end, it's a triangular coin, and then it only lands on this side or that side, right? So, okay. So, when you start, the chance of, there are 5 sides, right? This, the other 3 sides. When you start, the chance of landing on one of these 3 sides is a third. At the end, very close, the chance of landing here or here is a half, one here. So by continuity, there's some point in between where all 5 sides are equally likely. That's true. That's true. So what's wrong with that argument? There's nothing wrong with it. What's a little bit wrong with it is that where that break point is depends on how you're catching the coin. If you're letting it bounce around, or letting it land in sand, or land on your hand, or letting it land on a glass top table, those numbers would all be different. And that's okay. So but for any given condition, so coins can land on their edge. Here's a question. There's the other way that people, you maybe can't see it, but I'm spinning the coin around on its edge. Sorry, but it's spinning around. I promise you it's spinning around on its edge. And it lands heads or tails, of course. And so what are the odds of it landing heads or tails if I spin it on its edge? Well, there's a right answer to that question. You don't know, because you don't know. And people's guesses are all over the place, and In fact, coins spun on their edges are wildly different than coins flipped in the air. Coins have a very delicate center of gravity, how they land. So magicians have coins which are slightly shaved so that the center of gravity forces one side or the other, and they always come up heads. Right? And you can't feel it or see it. And coins, ordinary coins, the bias can be 80%. So that you can go try to find a coin, experiment around, and then bet your friends, bet. If it comes up heads, you pay for coffee. If it comes up tails, I pay for coffee, right? No, I didn't say that. There is a bias. Now let me screen forward, because I just said that, but like many things, there's a lot of stories I can't tell you. I had a class of kids. They were Stanford undergraduates. There were, I think, 103 people. And each kid, as a homework problem, had to take a penny and flip it 100 times, okay, and record how many times it came out heads. And this first picture is for the 103 coins. This is a graph that shows how many times among the 103 kids did the coin, how many times did it come up heads. And it's sort of symmetric in what you would think of, it's about 50-50, and then it's got some spread around it. I mean, of course, you're only flipping it 100 times. They took the same penny and spun it on its edge. And this second picture is a graph of what happened. What you can see is that that mostly mostly the coins come up tails, there's very few times that didn't come up heads very much. This is a very extreme bias, and that's it's hard to do the math of that, because it's a dynamical, real problem, and it's hard to figure it out. Okay, so here's a question that if I'd asked you this question before you walked in, you would have looked at me and said, "Are you nuts?" Sorry. Here are two things we could do. One thing we could do is that, okay, flip a coin, catch it in your hand. The second thing we could do is that. Okay, which is fairer? Okay, that's a question. And to most people, somehow viscerally, they think, well, coin landing on the table, on the floor, bouncing around, that seems fairer. To people, that's the reaction when I ask people. You can answer to yourself how you feel. But one reason I think that people think that a coin bouncing on the floor is fairer than a coin caught in the hand is when the coin is caught in the hand, there's a hand there, right? So somebody could, something, right? Let's neglect that, okay? That is, suppose that you're not trying to cheat yourself. You're thinking, when I flip a coin, which is it fairer catching it in my hand, or is it fairer letting it bang around on the table? And the point is, when a coin lands on the floor, and I've watched them carefully, some of that edge stuff, some of this stuff comes in. And so the coin, before it dies, spins around on its edge a little bit, and it has some of that bias is there, and it's really seems to be there. I'll go back to where we were, or try to. So that's point 8. Some of the coins spun on their edges carries over to coins bouncing on the table. Fact 9, it's a little theorem, but sometimes when people think, well, okay, you want to talk carefully about coins, maybe you could load a coin. You can load dice. Can you load a coin? And you can't load a coin. That's a theorem. That is, you can make a coin, quite inhomogeneous, and as long as you do that with it, you can prove to very, very good approximation that no matter how you do it. And I tried it. I had my physics guys make a coin. The bottom half was balsa wood and the top half was metal. And they just, we flipped it 1,000 times and it came up heads around half the time. So the inhomogeneity doesn't matter in flipping a coin. So, now 10 is a long story, and I'm only going to tell you one sentence about it. When you look at a high-speed picture of coins moving around in the air, they don't just go through turn like a plate that way. They process. They do very complicated things, and it's hard to picture. And the paper that I showed you about with Richard Montgomery and Susan Holmes did the mathematics and experimental mathematics of real coins in three-dimension processing. And we did experiments, and for people who know what the words mean, all of the physics is just fine, but if real people are flipping coins, they have different strengths and different proclivities. And what we needed to know is, what's the distribution of the angular momentum vector when real people flip real coins? And we were able to measure it by taking high-speed, slow-motion movies. And it's a long story. The bottom line is, when real coins are flipped by you, the chance of their coming up the same way they started, they're not biased towards heads or tails, but if they start up heads, they're a little more likely to come up heads. And a little more likely is 0.51. Now, of course, it's not 0.50000. Probably doesn't sound right. And it's not. That is some of that. And it doesn't matter. You can flip the coin up to the moon. That is, it doesn't matter how hard you flip it. When coins are flipped the way people do, there is a very slight bias. But it would take, hundreds of thousands of flips to detect that bias, and so maybe p is a half is not so bad. Okay, so now I've just told you some stories about flipping a coin. When somebody tells you stories, and it's natural to ask, yeah, but is it really true? I mean, that's a question you should always ask. Don't stop asking that question. And yeah, it's true. This paper just appeared in the Journal of the American Statistical Society. Fair coins tend to land on the same side they started. Evidence from 350,757 flips. And some people, because that 0.51 is a prediction of what would happen, and these experiments, they got high school kids all over Germany in different high schools, and they coordinated, it's a lot of coin flips, 350,000 coin flips, and there we are, Diaconis, Holmes, and Montgomery, and they verified that their coin that coins, when routinely flipped, have a slight bias to come up. So at least in that sense, there's still interest in this question, and now I want to point out something to you. You've just been listening to somebody talk about flipping a coin for half an hour. So I better change subjects. So but there's more to think about, and the simplest careful analysis of what makes things random, shuffling cards, rolling roulette balls, any throwing dice in Dungeons and Dragons or however you throw them, all of them are complicated and can lead to interesting math and interesting experiments and interesting ways of thinking about what it means to say things are random. Okay, so here's a complete different subject, but it's important because it's as close as I can tell you to where I think randomness comes from. So the dart in the wall. So suppose I had a dart, okay, and that wall it is a wall, but the left half of the wall was painted black and the right half of the wall was painted white. Okay, suppose for a second. And if I'm throwing the dart from here, well, it's not very random. I'm not throwing it randomly. I can make it come up black all the time. We all could, right? But now, suppose I rearrange the paint on the wall, okay, so that it's in stripes, the same amount of black and the same amount of white, but half black, half white. But if they're a foot apart and I'm here, well, maybe I could be pretty good about it. But now, suppose it gets to an inch or 1/100th of an inch, right? As the stripes get closer and closer together, and they're black, white, black, white, black, white, as the stripes get closer and closer together, it becomes 50-50 whether you land. No matter how careful, no matter how skillful you are, it becomes. So that's a kind of emergence of randomness. I'll tell you how it applies to flipping a coin. We're not done flipping a coin, but so that's what I mean by the dart and the wall. So let me. Okay. When I release the dart, okay, there's some angle, and I'm going to say it starts at 0 and ends at 1, but there's some angle that I release the dart. And suppose, I'm trying to aim someplace, so maybe the propensity of the dart to wind up someplace is different than other places. And so this is a curve that's supposed to represent the probability of the coin, landing that far over. That's how high the curve is. And underneath is the ruling. And what you can see by common sense is if the black and white splotches are small enough and all of the same size, then as the mesh size goes to 0, the chance of the coin landing in red or one of the two colors tends to a half. I mean, that no matter how wiggly the curve is. So that's kind of common sense. And mathematicians, just to show you what we do for a living in one slide, in a certain sense, I'm going to prove a theorem. Not really, but yes, kind of. So look at the chance. I'm calling them red and black here. H is how big the little bars are. So H is tiny. H is going to go to 0. The chance of red minus the chance of black, well, that's the difference between the area under the curve over the red places and the black places, and you can bring the absolute values inside. And as H goes to 0, that tends to 0 as long as your curve is continuous. That's called the modulus of continuity. If the curve had a derivative, then you can get a rate of convergence. And in fact, it doesn't even have to have anything like anything. It can be almost any measurable density, because translation is continuous in L1, but forget about that. So this argument that you can quantify the onset of randomness is called the method of arbitrary functions, and it was pioneered by Poincaré, a great mathematician of the last 2 centuries ago, and Eberhard Hopf and other people. That is, my density function is arbitrary. It doesn't matter how accurate you are or how careful you are. If that mesh is getting close to 0, it goes to 50-50. You can apply the same analysis to any kind of random phenomena. For example, I don't know if people know, there's a notion of a roulette wheel, and so Well, when I was a beginning assistant professor, a group of us realized, hey, you know, roulette is a physical game. So how does roulette go? There's a wheel, and then there's an inner wheel, and it has 38 slots in it, and a ball is flipped around the outer wheel and goes around, and then the inner wheel is spun the other way, and the ball eventually settles down by gravity and winds up in one of the 38 little slots that are there. Well, it's a physical game, and in roulette they let you bet quite late. You can watch. You're allowed to watch, and you're encouraged to watch, right? And then, well, can I really watch? You know, well, I can. So we built a little helper for the watching. It was something a little bit bigger than this, and what it was you, well, we figured out the equations, but when the ball went around a fixed point in the room, like that corner, we push a button. And of course it was under our shirt, and you have to tap your arm or something like that. But okay, push a button. Oop, and didn't want to do that, but I'll go here. And then when the ball comes around again, you push a button again. So the gadget knows how fast the ball is going. Okay? And then you do the same with the inner wheel. The inner wheel, when zero passes a point, you push a button again. The gadget knows how fast the wheel is going. And then the math allows you to know where the ball is going to drop. Now, this is very complicated to actually carefully do that, but we did pretty good approximations. So the math only gets it right. You get it right within half a wheel. Okay? But if you're getting, 35 to 1 on an 18 to 1 shot, it's like having a vacuum cleaner in the casino, right? I mean, it's just, you have an enormous advantage. Well, we not only thought about it, we went and did it, and that's a long other story. The first thing we did is we figured out the equations as math, but then we rented a roulette wheel and we got it leveled up, and we started to measure and practice, and our equations were wildly off. They just had nothing to do with what was happening with real roulette. And why was that? Well, we neglected friction, I just did before, and it turns out there are three kinds of friction that are important. There's rolling friction, there's sliding friction, and there's air friction. And the friction that really mattered was air friction. So when they turned on the air conditioners, all the equations had to change. Okay. But having done the math, what we could do is in the casino, we could tune our equations. They had some parameters in them, some choices, and make them match the actual wheel that we were using. And we went and made money. I don't recommend it. It's very stressful having a computer in your pocket and being in a casino, because maybe they'll break your arm if they catch you or something. They don't like it. And actually, it's against the law to bring in electronic aids now, but not when we did it. Okay. Before we did that, we did, probably everybody's seen a carnival, and there's a big wheel, and it spins around, and there's numbers, and it passes a clicker. That's much easier than roulette, right? It's click, 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 click. It just goes around, and then you can win a terrible prize, or something like that. And we did that, and we could win prizes every time. So okay, not anything. I'm not going to tell you about it, but you can do the same analysis with dice. I'm happy to talk about it afterwards if you like, but both fair and crooked. So, of course, what I was talking about with flipping a coin, it was a fair coin, but so a die, when you roll a die, what can come out on 6 faces, and there are different initial conditions, and then the die tumbles around and it comes out. So you could do a similar analysis and use the method of arbitrary functions. But also, sometimes casinos use shaved dice. So here's a question. An ordinary casino die is 3/4 of an inch, 0.750. Very carefully machined. Well, what they do is they cut off about 1/100 of an inch. So the top and bottom, the 6 and 1, they're the same sides, but these 4 sides are littler, right? And it stands to reason that if you roll a die and 2 of the faces are big and 4 of the faces are little, it'll probably come up on the big faces. Well, how does it play out? That is, because they also don't let you bet the way you'd like, and can the change in the odds overcome the house odds? So that becomes a math problem or physics problem. If you roll a shaved die, what's the chance it comes out on any of its faces? And well, we did the physics 2 different ways, and we made predictions, and then I wanted to test them out. And so, believe it or not, there are places that are called crooked gambling supply houses. Okay. Sorry, but it's true. And they're less, but they're around. You can find some in Manhattan for sure. And there are people who make shaved dice. Now, we were actually going to do an experiment, rolling the dice a lot of times to see if our equations worked out. Well, if you roll 10 dice at once and then count, counting error, somebody's counting, 2 people were counting, it's going to overwhelm any small edge. So I had an idea, which was the 1 and the 6 faces, the big ones, they have the same odds by symmetry. And so I made a big spot on the 1 and the 6. And the other 4 faces I left blank, so you could just count the number of spots. And then I had them very carefully machined, 1/100th of an inch off. And I had 100 dice made, big order. And I went in and picked them up. And this old dice maker said, I've been in this business a long time. And I said, what do you use these for? And I said, well, I'm a statistics professor. And he said, sure, buddy. Anyway, there's very, very nice stories, and I could give a talk of this length about dice. So suppose you wanted to read more about this. Well, a very good place to read about the method of arbitrary functions and really spells it out and does very careful error estimates is a book by a wonderful student of mine, Eduardo Engel. Group of Polish dynamicists wrote a book on the dynamics of gambling, and they tried to do bouncing and error resistance. And the best book for applied probability, the probability that applies to real gambling, is a book by Stu Ethier, a wonderful mathematician who lives in Las Vegas now, and it's called The Doctrine of Chances. So if you wanted to read about it, there's more to read about it. So, okay, shift of new talk starting. Okay, wake up, sorry. This thing, okay, so I lied to you. In order to communicate, you have to lie. That's a theorem. I said I was going to explain probability when I introduced the method of arbitrary functions, and if you listen carefully, I had that function f, and I said, well, it's the probability of the die landing there. So I was supposed to explain probability, and I snuck probability in the back door. So what is that f? What is f? Poincaré just didn't worry about it. Hopf said f is a continuous approximation to the long-run frequency, and that's okay. But to me, the argument seems to work for one flip, and so for me, f is my best guess. I think probability is subjective. And the method of arbitrary functions, the math I told you about, shows that f washes out. It doesn't matter what you think f means. And it gives a subjective version of objective chance devices. And so it was important. It was important in trying to make sense out of what does a person who, like me, think probability means in this circumstance. Okay, so here's almost the last topic. This question of, so actually it matters because gambling is a huge business, and you can do consulting, as I do, for casinos and get well paid for thinking about the kinds of problems I think about. But does any of this stuff really matter? Well, yes, and you need to get on board. It seems to me that if you look out at what people are doing with math about real-world problems, in addition to many good things, we're facing an epidemic of wild misuses of probability. People just introduce probability models, particular in finance, but in many, many areas, in predicting gas reserves and predicting how many helicopters to send on a mission. People make assumptions about randomness that they just don't make any real sense. And often these models that people make up have hundreds or now millions of unobserved parameters. The input comes from other models. The output isn't comparable with reality, and it's very, very hard to know what people are doing. And in case you think I'm making it up, here are some examples which I thought were important. This one, from mouse to man. So how much of a chemical, how much carbon monoxide should we allow in the atmosphere, or how much chemical should we allow in water? Well, what people do when they do experiments is they do careful experiments on mice, and then they figure out how much bad stuff hurts how much, and then they try to extrapolate. Well, in order to extrapolate from mouse to man, you need some equations. It's not free, that extrapolation. And first of all, the mice that they use are these very carefully bred laboratory mice. If you breathe on them, they fall over. We know we can extrapolate from mice to rats, actually, because you can do those experiments, and you really can't. And the predicting safety of chemicals that is the standard, extrapolating from mice to people is just in wild disarray. And if you want to see a careful discussion of it, this paper by David Friedman has people on the cancer side and people who think critically about models arguing with each other in a meaningful way. Census adjustment, that was a big one. So every 10 years they take a census, and they miss people. They miss something like 8% of the population in the census. A lot of people, illegal aliens, don't want to be counted. They miss people in the census. And what do you do about that? You know you're missing people. What do you do about that? Well, what the government does is they make up models, and they're just wildly made up models. If you look carefully at them, I've been testified in court about them, and then they use the predictions of those models, and it's just crazy. I'm not the only one to complain about it. There's this thing that's called the replication crisis. If you haven't seen it before, my friend Ioannidis wrote a paper called Why Most Published Research Findings Are Wrong, and he took the 100 most cited papers in the Journal of the American Medical Association, and he tried to replicate their findings, and about 30% were replicable and 70% weren't. So, people are using math to say, and statistics, probability models to say crazy, crazy things. If you want to hear more than I have the time to tell you, there's a wonderful podcast and website. It's called Calling Bullshit, and it's Carl Bergstrom in University of Washington, and he takes published findings and he rips them to shreds when he can, and not always, but often you really can. And so here's my last slide, and the main points that I wanted to make are, so probability isn't a black box. We can and must look inside to try to guide its sensible use. If you just say, well, I'll just put probabilities on everything, you're probably going to do nonsense. In case after case, and I just told you a few cases, when you look carefully, things can be done well, but most often we're lazy. And even when you think it matters, how many times should you shuffle a deck of cards? Or, is the coin flip in the Super Bowl random? No. We're lazy and they're done badly. I haven't time haven't had a chance to tell you about it, but I find the Bayesian interpretation of probability and statistics helpful in making sensible use of probability and protecting us from silliness. So those are main messages. If you wanted to look, I wrote a paper in a philosophy paper. It's called A Place for Philosophy, in which I have lots of other stories of this type. A very careful attack on big knee-jerk models that's really intelligently done and has both sides talking to each other, as David Friedman's book, Statistical Models, Theory and Practice. The stuff I told you about coins and dice and wheels, the paper I wrote with Susan Holmes and Richard Montgomery has all kinds of stuff I haven't had time to tell you about. My heroic publication that appeared in last year in the Journal of the American Statistical Association. And if you wanted to learn something about what do you mean Bayesian, what's subjective probability, is that sensible, I try to say it as best I could in a book which is called 10 Great Ideas About Chance, and I like it. So that's what I wanted to tell you about the search for randomness. I think you can tell it's been my search for randomness. Thank you for coming along.
Is there any random question? Well, I'll start with this one.
Oh, you'll get your chance, lady in red.
For the machine that does the coin flips, and you said it always lands on heads, does it depend on what it starts on, like tails or heads?
I started it heads up. Right.
Oh, you started heads
up. It
up.
always lands the side that you started up. That's a good question. I should have said it more clearly. Right.
Okay.
Right. Because otherwise it's contradicting what I said. No, but you know, I hope it makes sense. That is, if you hit something with the same force at the same place, it does the same thing. It's physics. But it actually works. It's unnerving to see it. Even for me. Go ahead. Hi.
Hi. Well, who's your favorite magician?
What was my
favorite magician?
I was a magician. Story in brief is when I was a kid, 5 years old, I could read, and I found a magic book. And my mother had some kind of summer camp, and I did 2 tricks for the other kids. And I was the center of attention, and they were awful tricks, just painful. And but that was my hobby. And then for birthdays, I'd get presents. And then I lived in New York City in Manhattan, and I found a magic club, and I joined. And there are magic stores. There are magic stores throughout Long Island too. And then when I was 14, maybe the best magician in the world, a guy named Dave Vernon, asked me to come on the road with him as his assistant. And I didn't ask anybody. I just packed a bag and met him on the West Side Highway, and off we went. And so I was traipsing around the country as a magician's assistant for 2 years, and then I came back and I made my living as a magician for 10 years. And then when I was 24, I wanted to learn, not to read and write. I knew how to read and write, but I wanted to learn some things, and I wanted to learn probability because magicians are very interested in crooked gamblers, and so we would seek them out. And crooked gamblers had tricky bets, and I'd gotten good at figuring out the odds of tricky bets. But I wanted to know how I was doing it and what the math was. And somebody told me, oh, there's a best book on probability, and it was by Feller, Introduction to Probability and Its Applications. And I got a copy when I was 24, and I tried to read it, and I couldn't read it because I didn't know calculus. So I decided to go to college to learn calculus so I could read Feller, and now I teach out of it. And then I got interested in math, and I'm still interested in math. I'm still interested in magic too. I don't do much of it. I invent magic tricks for other magicians, but performers, we're going to have a piano concert, right? There are performers and composers. So in magic too, there are people who invent tricks and people who perform them, and they're different. So it's still part of my life, but it's mostly I find mathematics and the ability to understand the world through mathematics just as magical as anything. Hope I made you see that. I tried.
Hi. From the outline, I see the part called the philosophy points, and I'm really curious about that. Could you elaborate how the flipping coin is related to philosophy, and what's your point?
Well, yeah, let me try to, so I hope the mic is good, you could hear the question. How is flipping the coin related to philosophy? Well, if you pick a statistician or a probabilist at random, and you find some professor who's teaching probability and ask, what does probability mean? They say, oh, if you do it a lot, it happens that proportion of the time, right? But let's just think about that a little bit. For example, I had a guy, when I was a graduate student, he came in and he was a retired executive from life insurance company, and he liked to roll dice. And he rolled dice, actually 3 million times. And he was testing the laws of chance. And when you roll a die 20,000 times, it gets round. The corners bump off. And if you're flipping a coin a lot, well, the psychology, I just flipped it hard. Next time I'm going to flip it not so hard. I don't have to flip it hard every time. And so the notion of frequency, long-term frequency, doesn't make any sense. In the long run, we're all dead. I mean, the reason probability is useful is that it works for 1,000 or 20,000, things like that. It doesn't. The notion of justifying something which is non-verifiable, you can't flip the coin. You get tired, people get old, they change, basketball shots. After half an hour, the chance of getting the ball in is different than it was when you started. And at the beginning, it's different when you're warming up than in the middle. So does it make sense to say that there's a constant probability? So the ordinary frequency definition of probability doesn't make any sense to me and many other people. And there's another way of thinking about probability which builds in the idea that probability is a statement about an observer's uncertainty. And you might think, well, people are different. Yes, people are different. If I'm flipping a coin and you know about me, well, I can probably flip the coin and make it come up heads every time, right? But if somebody doesn't know about me, well, he's flipping a coin. It's 50-50. Of course, what you know affects things. And so subjective probability, Bayesian probability allows you to build that in, and then it makes math, and it explains, as I tried to explain, when frequency makes sense, when the initial conditions, your prior distribution washes out. So I can't say it more in a minute answer to a question, but that's what our book was trying to do, 10 Great Ideas. It's a chance, course we teach in the philosophy department, and it tries to say, here are the different ways of thinking about probability. And the coin tossing is an example everybody uses. I mean, it's inside of us, flipping a coin, or that's a random phenomena. And then you can illustrate that different interpretations of probability lead you to different conclusions. So I don't know if that helps, but if not, and it's a good question, look at item 5. Hi.
So you said that coins can't be loaded, like
cannot be loaded. Right?
Why? Like how?
Why not? You mean?
Like I mean, I don't know if it's like
you can try. First of all, you can try it and you can't do it. So that's the first thing.
Right.
I tried it and I couldn't do it. But it's a theorem, and why is it? So it's a theorem, so I can prove it. And,
right.
The proof runs this way. Because the coin, so suppose the top of the coin is lead and the bottom of the coin is balsa wood, right? That's one image. You could make other images. But as long as the coin is spinning around and access through it, that's not going to matter, right? That is, how many, because it's spinning around, and the flip doesn't, the spin that you give it isn't affected by the fact that the top is balsa wood or not. But to actually make a careful statement about that, it's a math problem. Good for you for wondering about it.
Right.
But even we can make, the inside of the coin really quite inhomogeneous, and then do the analysis. Now, it's not perfect, but it is, to the degree of approximation I'm doing here. That is, if the coin is vigorously flipped, answer in a slightly different way. I had a friend who used some of this probability stuff for a class of high school kids, and he had them flip a coin 100 times and catch it in their hand. And he showed me the results, and they were very patterned. They were head, tail, pretty patterned. And it was so patterned that something was wrong. And so I went in and watched them flip. And the thing was, they were bored silly. And they were just doing little flips. Well, it goes over once, right? So if it came out heads, next time is tails. And to sum up, so the actual physics matters, and so I don't know. But there's certainly a reference in our book to the two careful papers, and we did one too, that show that they can't be. But it does sound, you think, well, heads, protrudes more and tails less. Coins spun on their edges, it's completely different. Then balsa wood and that would work. And so therefore coins spun on the floor could be loaded. But coins that done with, they're fared a very good approximation. So.
How do you tend to understand probability as it relates to systems without clear inputs? Where for a coin flip, there are physical measurements that can be taken of a coin. How do you understand it for questions of say human reaction to something, or
Sure.
questions of mind?
So yes, so we assign probabilities to all kinds of things. Should you come to this lecture? Is it going to be okay? Is it going to rain? Should you take this class or that class? Will Trump last out his term? Okay, no, but I mean, you can make bets on that, right? And so we assign probabilities to things which you can't measure the initial conditions, and frequentists can't touch those problems, but subjectivists can, and bookmakers can, and so we'll try to assign probabilities to almost anything, but of course they have their own way. We have their own way of saying they're uncertain. Instead of there being, for flipping a coin, my probability of around 0.51 is very, very peaked. For some other thing, even though I might say its probability a half is my best guess, but it could be very broad. but the setup of subjective probability allows you to assign probabilities to anything. And since most things that we want to assign probabilities to aren't like coin tossing, it's important to have a theory that touches those. That's why I like the subjective theory. But.
Okay, I think we can close it here. Thank you very much for a wonderful lecture.